My name is George Batchkala, and I want to present the work we did together with Sharib Ali for the Medical Automatic Polyp Segmentation Challenge. We used the standard unit architecture proposed by Roneberger in 2015, which has been successfully used for many segmentation tasks after that. The task focuses on two metrics, intersection over union loss, and it uses the dice coefficient to resolve ties. These are two of the common losses used for segmentation tasks. The challenges in optimizing intersection over union include that intersection over union requires binary masks as an output of the model. Binarizing IoU in turn reduces the gradient floor, which is inadvisable for training, while using non-binarized intersection over union is hard to interpret and hard to compare with the other one. Now let's go to experimental design. For training losses, we use the three that I already talked about, and for validation, we binarized the predicted masks and computed the standard intersection over union. We trained the models for 100 epochs and patients of 10 epochs. We optimized it with Adam optimizer with learning rates 10 to the minus 4 and weight decay of 10 to the minus 8. For pre-processing, we use standard unit pre-processing of 256 by 256 with augmentation including random rotations, horizontal flips, and cropping back to the original size. Here are the learning curves for the 4 experiments that we did for the 3 losses and for intersection over union loss with augmentation. The message of the slide is that augmentation brings the learning curves closer and helps to improve the generalization performance, which we can also see on the quantitative results presented in this table. We can see the intersection over union of over 0.7 and the dice coefficient of 0.7879 for intersection over union loss with augmented, which is better than the other 3 experiments we performed. Now let's go for some qualitative examples. Here we present 5 best examples on the validation set, which are different, which have polyps of different sizes, where they're in various locations in the colon, and additionally, different textures are present in the protrusions. We see that our method is able to segment these polyps accurately with the intersection over union of nearly over 0.95. Here are some of the examples on the test set. We didn't have the ground truth segmentation mask, but visual inspection suggests that our algorithm can accurately predict most protruded polyps. However, the method confuses the large polyp structure with the colon folds in the right example. And now some plans for improvement. We want to try it in the future. We want to try different IoU, different unit architectures, try different downsampling layers instead of max pooling, maybe inception blocks or dilated convolutions, and try to introduce attention to focus on the important areas of the images. Thank you very much for your attention.